This conference will now be recorded.
Okay, welcome everyone. Today we will have a presentation by Amit Oren from Broadcom about transparent clocks. But before we kickstart, we need to do some announcements. So we had our DC TAP DC PTP DC profile approved like last week, and I wish Michel was here. He was able to share with more details. Alad, would you like to explain a little bit more about the profile?
Yeah, thanks, Ahmed. So this is the fruit of a second work stream, and basically the first PTP profile centered to data centers. We've had different profiles for many years, and there was none that covered the requirements when it pertains to data centers, especially when it comes to scale out data centers. And this is the fruit of some 7 different companies and different contributors who helped influence the spec and then come up with the requirements. This is just the beginning of the PTP profile. We have up next, we're going to take it with the IEEE and also implementations, further implementations when it comes to PTP4L.
Also,
up ahead.
if you want to contribute, again, the PTP profile is more like a living document. It reached a point that this got approved and so on. It has even a IEEE CID. If you want to have comments or you want to contribute on it or so on, you can reach out to Michel, or simply you can go on GitHub, try to do a fork, and then like put comments or whatever, so you can find it on the OCP GitHub, or we have like all this other links like timingcard.com, we have opentimeserver.com, like all of these things will link you back to the same GitHub, so you can take it from there.
Also put on the chat box, I put the link into the contribution. It has all the TAP contributions there. And yeah, the request, as Ahmed said, is the ask is really it's open. It's open for your contributions, open for your influence, and we look forward to solicit feedback.
Yeah. Okay, so with no further ado, we'll introduce Amit Oren. Amit is an architect in the core switch in Broadcom, focusing on 5G infrastructure and synchronization. So I mean, I learned a lot of things about transparent clocks from Amit. So with no further ado, Amit, the floor is yours. So let's make Amit a presenter.
I will do that. Amit, it's yours.
Okay. So 1 second, let me find the window. Okay, so can you see my slides?
There is a button that says share screen. Yes, now
it's up there.
Okay, so thank you very much for the opportunity to present here at OCP TAP. I represent Broadcom's Switch business unit, where we have been involved with network synchronization technology for many years, many generations of the technology and many customers. And hopefully we can contribute to this OCP initiative. So the subject of the talk today is the transparent clock and its applications. I think that that there is perhaps a perception out there that the transparent clock is the less popular brother of the boundary clock, and it's definitely getting less attention. What we want to do in this presentation is to look in more detail at the transparent clock, and perhaps we can dispel some of that perception. So in terms of the agenda, what we want to try to cover today is to look at the transparent clock from the standards perspective, look at the different variations that we have for a transparent clock, some of the use cases, and some of the performance aspects having to do with synchronization and processing latency considerations. And once we figure out that low latency is important, we can look at how low latency implementation is actually accomplished, and then talk about scalability in deployment. And we're talking about deployment in data centers with a large number of slaves, of endpoints, and how that scalability can be accomplished, and what is the difference between a transparent clock and boundary clock in terms of that scalability. So if we look at how a transparent clock is defined in the standards, then it's defined as a device that measures the time it takes for a PTP event message to transit the device. This is also known as residence time, and then to provide this information to downstream clocks that are receiving this PTP event message, either to further propagate it or use it locally for synchronization. Right here, we already see a difference, right, between a transparent clock and a boundary clock, in the sense that a boundary clock is a device that terminates the PTP protocol on its slave ports and restarts or originates the protocol on its master ports. So if I see a sync message coming out of a boundary clock, I know that it originated in the boundary clock. This is not the case for a transparent clock. Transparent clock is a transit device. So if I see a sync message coming out of a transparent clock, it did not originate at the transparent clock. It originated somewhere else, and the transparent clock is a transit device that processes this packet but does not terminate or originate the protocol. So that is a very big difference already between a transparent clock and boundary clock. The standard actually describes 4 variations of a transparent clock, and these are the 1-step and 2-step, and pure delay and end-to-end delay. And these 4 variations are very different in terms of complexity of implementation and in terms of scalability of deployment. So we're going to look in more detail at these 4 variations. So first of all, to look at the timestamp processing aspect of 1-step versus 2-step. So if we said that a transparent clock is a device that measures the residence time and communicates this information to other clocks, then 1-step and 2-step are 2 different variations on how this information is communicated downstream. That in the case of a 1-step implementation, this residence time is actually accumulated into the correction field of the event message itself. And so as the event message is progressing or forwarded from the master to a slave node, then all these interim nodes will update this correction field. And the observation here is that in the case of 1-step, it's stateless in the sense that I can process the packet without having to worry about individually and without having to worry about other packets associated with it, like in the case of 2-step. In the case of 2-step, presumably the device, the clock device, is unable to process the event message on the fly and both compute the residence time and update the correction field in a way that will be accurate, and therefore in the two-step mode, it's a two-step process where I measure the residence time on the event message itself, but the communication to downstream devices is done by modifying the correction field in another packet called the follow-up message. So we already see a very big difference, right, in the complexity. Oh, sorry. In the complexity of implementation between a one-step device and a two-step device. Because one-step device is essentially stateless in the sense that once I finish updating the correction field of the event message itself, I'm done. Whereas in a two-step device, I need to store that information, wait until this follow-up message shows up, and then update this follow-up message. And when I have thousands of flows going through the switch or the device, this task quickly becomes challenging, right? I mean, I have to not only go fetch timestamps, measure residence time for each flow of many thousands of flows, I also need to store it in a database and correlate between this flow and other follow-up messages that may or may not show up. So this quickly becomes very difficult to implement. And in fact, the end-to-end two-step transparent clock is probably the most complex in terms of its implementation, whereas the one-step end-to-end transparent clock is probably the simplest because it's stateless and it can be implemented without any software intervention in the forwarding and processing of packets, because I can update the correction field on the fly in hardware and not having to worry about any software involvement in the process.
Yeah, Amit?
Yeah.
Yeah, hi, this is Michel. I have a question. I think, yes, what you said about the sync follow-up, I think for a two-step end-to-end, what's even more challenging is the delay response, delay request, delay response, because you need to measure on the delay response request, but you need to update on the delay response, which means that you need to keep state, not just for a packet that is about to leave, but you need to keep state for a packet that will be returning back to you and then update that packet, right? So, and so that's definitely another problem. But the biggest problem that we've seen from a delay request, delay response also is that in a data center network or environment, you cannot guarantee that the paths are going to be congruent. That means that the delay request and delay response are always going to follow, the same path. And if you cannot guarantee this, the two-step is a no-go.
Yeah, exactly. I agree with that. it makes the implementation even more complex than just worrying about the sync propagation. The delay request response adds significant complexity as well.
Right.
Anyway, in the case of one step, this is a lot simpler because both in the sync case and the delay request case, we simply update the correction field, and the master node, when it responds to delay request, it would copy the correction field from the delay request to the delay response, and so that information about the accumulated delay on the reverse path is actually communicated by the delay response, but was actually collected again in a stateless manner on the PTP event message itself. So yeah, so there is no question that a one-step end-to-end is significantly less complex than a two-step implementation. And again, especially if the if like in a data center, the two paths are not guaranteed to be the same, then it's practically impossible to implement.
Yeah, just to add, if I may, in the in the PTP profile, we added quite a lot of text on what you just explained. And one thing that we emphasized is if you're going to use transparent clock, that it's highly recommended that you use a one-step, because a two-step might break right away if you're not careful about some of the constraints in your environment.
Yeah, I fully agree with that. Yeah. So the other set of variations has to do with the delay measurement mode, whether end-to-end or peer-to-peer, and the standards define these two modes, which differentiate. But what exactly is being measured? That in the case of end-to-end delay, I'm actually measuring the residence time across the device itself. And in the case of a peer-to-peer transparent clock, I'm actually measuring the delay across the device plus the delay across the incoming link. So that would be the link where the sync message comes from. And as you can see, in the case of peer-to-peer, when I get the sync message, it already includes all the delay information on the propagation path, and there is no need or no missing portions, right? Because it includes both the devices themselves and the links associated with these devices. So by the time the sync message arrives at the OC endpoint, it's already accurate in the sense that it includes the origin time and a full account of the propagation time. So in terms of scalability, it's pretty clear that in the end-to-end case, the endpoint would be performing delay measurements all the way to the grandmaster, and that has to be a unicast transactions. Whereas in the peer-to-peer case, I'm doing delay measurements only to my peer node. So it's pretty clear that the scalability of a peer-to-peer implementation is maybe just as good as a boundary clock, in the sense that I don't have to go all the way to the grandmaster in a unicast transaction to do delay measurement, but rather I only do that delay measurement to the peer node. So if we look at these the table that we have for the 4 variations, we can see that we talked about one-step versus two-step, but we can also see that peer delay offers significant deployment scalability advantages over the end-to-end implementation, and so when considering transparent clocks, it's very important to understand the different variations and how they perform and scale. So the next thing we want to look at is the different use cases for transparent clocks, and perhaps the more well-known use cases are the ones that are standardized in ITU. So the ITU defined a profile as part of the G.8275 architecture for what's known as a telecom transparent clock. It's standardized by ITU. The performance aspects of it are defined in a standard called G.8273.3. And the way that it's defined is in ITU is that it operates in end-to-end mode only. And it has the option to use physical layer clock that is recovered from the Ethernet link, typically by a telecom PLL, and use that for synchronization in the case of full timing support. So the G.8275 architecture, actually, you can see several options here for deployment scenarios. So you can have a master that with a link that's composed only of transparent clocks, or combinations of boundary clocks and transparent clocks. If you are familiar with what the ITU is standardizing, it's actually backhaul links that provide synchronization to cell towers. And so there's a very large variation in the kinds of deployments that are considered by ITU, and these can be either fiber or microwave, and so on. And in fact, one of the examples that I can provide for that we actually have been involved in these use cases is a microwave backhaul link that provides, again, synchronization to a tower where the link itself is configured as a transparent clock between its two endpoints, right? So on the link itself, you have a microwave signal, but logically, from a PTP perspective, it behaves as a transparent clock in the sense that the two sides are synchronized. They can measure ingress and egress time and provide that information to the tower. So these are the important aspects. One should pay special attention to the fact that in the case of full timing support, it actually uses a telecom PLL for synchronization. That is not something that you typically see in other kind of deployments. Another very important use case for transparent clocks has to do with industrial automation, and especially the protocol that is used, that's called Profinet, which is an Ethernet-based industrial automation protocol. And Profinet uses 1588 for synchronization. But the deployment model is kind of unique in the sense that it doesn't use boundary clocks, but rather a TC, each node is a TC plus OC. So a transparent clock is there for the propagation of synchronization information across the chain. And we have an ordinary clock attached to each one of these transparent clocks for the purposes of local recovery of the clock. The industrial automation deployments are characterized by very long chains of transparent clocks. So like a number of 30 hops is not unusual. In fact, Profinet states that their goal is to support clock chains of 100 nodes with 1 microsecond accuracy. And the reason that they're actually looking at using transparent clocks has to do with the fact that contrary to chains of boundary clocks that exhibit a phenomenon called gain peaking, where in some wonder frequencies there's actually an amplification of the wonder. That's a phenomenon called gain peaking, and when you have long chains of boundary clocks, that accumulation can be significant. That TCs do not exhibit that kind of gain peaking, and therefore they're even more suitable for implementing very long chains. So there's been many studies on the performance of these chains of transparent clocks, and what you can see here is a typical example showing 30 hops with 200 nanoseconds of RMS time error across 30 hops, right? So if we have an RMS of 200 nanoseconds, it means that the peak error is about 3 sigma, right? 600 nanosecond, which is consistent with their goal of 1 microsecond peak error.
Hi, Amit.
In fact,
One question came in, whether the PTP support is part of the external PHY or an attribute of the switch ASIC. In other words, does it require a specialized switch system from your end?
No, that our switches naturally support the a one-step end-to-end TC with no in hardware only, meaning that you don't need to run any software to process packets or perform any kind of manual forwarding or anything like that. That the hardware is already supports end-to-end one-step implementation.
I see, and that's an attribute of the Tomahawk Trident ASIC, not some kind of.
It's actually an attribute of every single switch that we have since we started working on this technology many years ago. We support this one-step. We obviously opted for one step because of its scalability and the stateless nature of it. But since then we've been improving the performance and timestamping performance over many generations.
Got it. Thanks.
And finally, the last use case that I think is worth mentioning is that of time-sensitive networking. Time-sensitive networking is a collection of standards, one of which is the synchronization standard called 802.1as. And 802.1as defines these systems called time-aware systems. So like an example would be like a time-aware bridge or time-aware router, etc. And these systems, the profile, the 802.1as profile actually mandates a two-step implementation, which in retrospect may not have been the best choice here. And the reason for that is that when you have software involved in the forwarding and processing of every packet, it tends to increase significantly the processing latency. We will soon discuss the effects of latency, and we see that creates significant problems. But the reason I'm mentioning these time-aware systems is that in some aspects, they're very similar to peer-to-peer TCs in the sense that they measure both link delay and residence time. And so they actually can propagate a sync message and process it in a similar manner that a peer-to-peer transparent clock would process, namely that they account for the link delay and the residence time. But there is another aspect here, which is typically not part of a peer-to-peer or a normal PTP peer-to-peer TC, and that is the aspect of logical synchronization. Because of the significant processing latencies that the two-step processing exhibits, that the time-aware bridge actually measures two quantities or keeps account of two quantities that are important to keep the error low because of that significant processing latency. And these two quantities are the fractional frequency offset to the peer node So when I'm performing this link delay measurement, I'm actually not just measuring the delay across the link, but also the fractional frequency offset from the peer node, and knowledge of that fractional frequency offset and that of the fractional frequency offset across the whole propagation path from the master actually can tell me what is, by multiplying all these numbers across the path, I know what is the fractional frequency offset of the TC node relative to that of the master. So again, I'm measuring not just link delay, but also fractional frequency offset to the peer. And then using, and since that process is done by all the nodes all the way to the grandmaster, then by knowing this fractional frequency offset along every node in the path, I'm able to infer what is the fractional frequency offset between the time-aware bridge and that of the master. And both quantities are important to correct these measurements and remove the effect of the frequency offset of the oscillator, and avoid these accumulating large errors. So the typical usage cases for these for TSN and its predecessor AVB, audio video bridging, is actually things like automotive entertainment. So you can have an implementation where you have where this protocol is being used inside of a vehicle to actually connect cameras and entertainment systems and so on. And for the kind of accuracy goals they're looking for, this logical synchronization can actually achieve reasonable performance. So we can see maybe tens of microseconds of accuracy. But again, having spent many hours debugging these implementations, I can tell you that nothing good comes out of large processing latencies. That makes everything a lot more difficult, and performance is always more difficult to achieve than a low latency implementation.
Amit, one question. Is that related due to the fact that the one-step method is basically a forecaster? I mean, we're dealing with causality. Packet didn't leave yet, and then you are putting the correction field in it saying, oh, it arrived in this. Like you basically have that correction field stating something that's in the future. Is that one reason for that?
Well, I think, I think, one thing that you can say about the difference between one step and two step is that the information about the residence time, there's no delay between that information and the event message itself, right? So you're required by the standard to timestamp an event message on both ingress and egress. When you want to recover time, you need to use these timestamps, and when you have the information immediately available to you about the path delay together with the timestamp, then you don't need to wait for another message to do your servo or clock recovery processing, right? When you have this information about path delay comes on a different packet, and there may be a difference in the arrival time between the event message and the follow-up, that can delay, right? Introduce delay in the processing of the clock recovery. Now, because this is a closed loop and delays are never encouraged when implementing closed loops, then I think that's where the problems, or the differences might arise, right? Is the additional delay incurred that it takes until you can actually get the information that is transmitted by the follow-up. That's the issue. I think when you talk about low latency, it's the low latency in the event message, right? That's the key. But the delay in the information, in the timing information carried by the follow-up can actually means that you cannot begin the processing immediately when you get the event message, but you have to wait for another packet, and like who knows when that's coming, right? That's the issue more than anything else.
Okay, so like back to let's say the one-step message. Sorry, this one-step method where we place the residence time before the packet leaves. So there is here, let's say, an assumption of like when you're placing the correction field, you're assuming that because the departure is happening in the future. So that constant that you place there, is that something that you get due to like from calibration? Is that a dynamic thing that gets calculated all the time? Is it just placed once there?
Yeah.
So anything you can shed light on that?
Yeah, you're correct that when you implement one step, then that if you look at the PHY and the MAC and exactly where the timestamp is generated and the time it takes from timestamp generation until the packet actually hits the wire, that this delay is not necessarily constant. In fact, it is not constant. And if you are seeking to implement accurate implementations, high accuracy implementations, that you actually need to account for that delay. And actually, when you're doing the update of the correction field, you need to, it's different per packet, and it may have to do with how much delay the packet is actually going to see between the timestamping point and the wire.
Yeah.
And you have things like synchronization markers. You have all these clock domain transitions and things that will affect the delay seen by the packet. And you have to do the best job you can to account for that if you want a very high accuracy implementation. That is, when we say that we've invested in this technology many years, I mean, that's part of it, right? That, that a switch, that the port speeds can range, from a gigabit to 100 gig, and or 400 gig in multi-lane and so on. That you have so many speeds and so many modes that this becomes very challenging maintaining the same level of performance across all these different combinations of port speeds and port modes that is a significant investment that we make in maintaining this level of accuracy.
And then one last thing, like when we are like basically in packet is in the residence, so you're basically counting the time with the clock with the oscillator that you have on the switch. So this oscillator never gets the chance to be
Yeah.
synchronized. So is there?
Yeah, this is the next thing you want to talk about. Is
Okay, sure.
excellent question. Why? Because we want to talk about synchronization and processing latency and how that affects the performance of the transparent clock. And as you point out correctly, the transparent clock measures the residence time by timestamping the event message at the ingress and egress ports of the node, and calculating the difference and then communicating that. And as you point out correctly, the measurement of this, of this time interval relies on a local oscillator that, in most cases, is not synchronized to the master frequency. One exception that we saw, right? that we talked about was the telecom transparent clock that uses synchronous Ethernet for synchronization. That would be an exception to that, but in most cases the TC is not synchronized. And the oscillator is free running, and therefore it exhibits some frequency offsets that can range, depending on the quality of the oscillator, can range from tens of ppbs, parts per billion, to tens of ppms. You know, in Ethernet, it's not rare to see 50 ppm or 100 ppm oscillators that are being used, and when I measure these time intervals using an oscillator with a frequency offset, I have an error, a measurement error, and that measurement error is equal to the time interval that I'm trying to measure times the fractional frequency offset of that oscillator. So as an example, if I'm measuring in 1 millisecond interval and my oscillator has 100 ppm offset, then 1 millisecond times 100 ppm is 100 nanosecond, and that would be then the measurement error. And a number like 100 nanosecond, when you're trying to achieve, accuracies, like in telecom, which might be less than 10 nanosecond, then that is, very significant error. Right, I can try to improve or reduce that measurement error by using perhaps a better oscillator. So a very common better oscillator might be a TCXO with a 4.6 ppm instead of 100 ppm offset. In that case, with the same 1 millisecond interval, I can get an error of 4.6 nanosecond. But generally, the observation is that to mitigate the effect of these measurement errors and to avoid the need for synchronization, that it's important to reduce the residence time, because obviously if my residence time is 1 microsecond, then it's very hard for the oscillator to introduce large errors. And this is the reason that end-to-end transparent clocks that where all the forwarding is done in hardware and can keep the residence time low will have much better performance and much less implementation issues than software-based implementations like 802.1as or a two-step transparent clock that, in addition to all the scalability issues, also have a problem with large or high latency that starts to introduce problems having to do with the oscillator and its synchronization considerations. So again, it's important to consider both the latency and the oscillator performance, basically to avoid the need for synchronization. That if I keep the propagation time low, then it doesn't really matter if I have 100 ppm oscillator.
My bigger problem here is it's very hard, or I mean, like next to impossible, to detect this misalignment from the ordinary clock's side, because you just get this correction field and you take it as given.
Right.
Yeah, you don't see any variation. You don't see anything in the variance in the histogram.
Right.
You don't see anything.
See an error.
Yeah.
Yeah,
I mean, unless, I don't know how that works, unless you go, for example, different pathways to just do probing, let's say, and then you compare different pathways that they include, let's say, different transparent clocks, how, like, let's say, consistent the results are.
Again, if my propagation delay is 1 microsecond and I have 100 ppm oscillator, then
yeah, I agree. It all depends on the residence.
0.1 nanosecond. It's completely insignificant, even across several hops, right? It's
Absolutely.
something, and that's the key, right? The key to getting good performance from a transparent clock is either you know how to synchronize it, or you keep the latency low, which means that avoid software implementations as much as possible. And that is, in my opinion, the reason that these 802.1as implementations, that they modify the sync messaging software and they introduce significant delays. I mean, 1 millisecond is not uncommon. I've seen much worse than a millisecond in terms of processing, and that's how you get in trouble, right? That's why you need logical synchronization and so on, and so you're always going to get questionable, performance because of this high delay. So avoid delay, and some of the means that we have implemented to reduce the delay is, first of all, primarily a hardware update of the correction field in both unicast and multicast forwarding. So in the case of multicast, I can have a sync message coming in, and the sync message would be replicated to multiple output ports, and the correction field updated on each one of the egress ports individually. So this is both a scalable and a high performance manner of dealing with, of implementing this low latency. Of course, if you want to support peer-to-peer delays, that you're going to have a software process that basically per port software process that conducts these peer delay measurements, which again have to be implemented with low delay for the exact same reasons. And having a hardware register that keeps track of this measured link delay, so that again the hardware update of the correction field can account both for the residence time and the link delay, can again help in reducing the latency. Obviously, to deal with congestion issues and latencies induced by congestion, that classifying the PTP flows into high class of service queues that can help in reducing transit latencies is also important.
Just to add, if I may, in the PTP profile that we worked on for data center, we exactly called out that obviously if you use an end-to-end transparent clock, it's highly recommended that you if you use, let's say, IPv6 mapping, that you classify in the proper TC or traffic class, right? And then we, in the delay budget, the time error budget exercise that we did, we took plus or minus 100 ppm, like you had in your other chart, and then we called out a residence time of 100 microsecond, which obviously when you do the math, it becomes insignificant, like you said. Yeah, the contribution of that error due to the transparent clock or the use of a free running oscillator with a switch that has, that is very, very high speed. Yeah.
Yeah, 100 microseconds is definitely very high.
Yeah, so we took a very conservative number here just to show that still the residual error is very, very small.
Yeah.
Yeah, a quick question. How consistent is the propagation delay through one of the switches? I mean, with congestion buffering, with sort of incremental delays.
Definitely an issue, right? Definitely an issue that in the case of congestion, if you're queued up, there is no, unless you're classified into a high class of service queue that with appropriate prioritization, it's very hard to guarantee anything, right? That congestion will modulate the delay. And so the error, because it's a product of both the oscillator offset and the delay interval, that if that changes, the error changes. So the error is actually modulated by this congestion, making it even more difficult to remove by an endpoint or filter out by an endpoint. So yeah, that is an issue, and you can say, right, that maybe the implementation choice for the telecom transparent clock that uses sync-key and synchronization basically removes that issue. Is not such a bad idea. Because it can deal with, it can deal with any kind of error modulation by congestion. So again, for the final slides, we want to look at the scalability aspects of a transparent clock deployment and the perception that boundary clocks might be more scalable than transparent clocks. I think some of that perception comes from the fact that boundary clocks actually perform the master function for all the downstream nodes. So they basically offload the master workload from a grandmaster by serving all the downstream nodes. Whereas the perception is that a TC will be viewed as less scalable because all the endpoints actually run a delay measurement all the way back to the grandmaster. But as we talked about previously in the presentation, this is only true of end-to-end transparent clocks. That peer-to-peer transparent clocks can be just as scalable because a server endpoint or ordinary clock endpoint conducts the delay measurement only to the nearest transparent clock, not all the way back to the grandmaster. So in that sense, is just as scalable as a boundary clock. The workload associated with this pure delay measurement is not very significant. I mean, we've seen implementations that perform these delay measurements once a second. So you basically have a process that for each port of the transparent clocks performs delay measurement to a peer node once a second, and that provides very good performance because again the delay of the link again is not subject to congestion. Usually it's the queuing structure in the switch, not the link delay. So you get a pretty stable measurement even if you run it once every second. Right, we talked about the fact that the sync message can be multicasted, and therefore the GM can send few copies, right, of a sync message that they can be replicated and multicasted to across the TC tree to all the endpoints. And so there's no significant workload to the grandmaster associated with sync propagation. The GM has to worry in terms of delay measurements only to the directly attached transparent clock. So again, it's not a very high workload associated with that delay measurement. And as we saw for Profinet or industrial automation, that TC plus OC model can be used for those switches that actually have to recover time. So if my switch, if I want to implement telemetry or things that require global time, then in addition to the TC, I can add an OC that listens in or sits on one of the ports of the transparent clock, logically sits on one of the ports of the transparent clock, and then recover time for the benefit of things like telemetry. And then again, unlike a BC, which always recovers a clock, TCs that do not recover clock and don't need to know what time it is, if you have the ability to control the latency, then you can actually opt for less expensive oscillators, right? That you don't, if you're not implementing an OC, and if you can guarantee low latency, then you can actually compromise on your oscillator. So, all in all, I think that there's no reason to believe that peer-to-peer TCs are any less scalable than BCs for deployment in a data center. And in fact, if you look at all the body of publications coming from industrial automation about long chains of transparent clock and the fact that they have good performance and stability, then there is, with the modest number of ops in a data center, much less than industrial automation, then there is no worry, no worry about performance. Again, if you can control your latency and or your oscillator quality. So I think that is the last slide. I'll be happy to answer any questions.
Excellent. Thank you very much, Amit. So, is there any question? Please just unmute yourself and. No? So one question I had, so if you want to go, let's say, Amit, with, let's say, the residence time, reducing your residence time is inevitable, and we want to have somehow a method that we introduce synchronization to the transparent clock. What are, I mean, first of all, is there something that is like relatively standard to do that? Is there a way for it, or it's going to be like?
Yeah, so we talked about two ways to do that, right? One way is the one that the ITU chose, which is to use Sync for synchronization. That is definitely the best you can do in terms of the performance.
Yeah.
And the other way, which is the way that was chosen by 802.1as, which is logical synchronization. I can tell you that from the many hours we spend debugging these 1AS implementations, that's never going to be as good as Sync-E. And like I said, if your goal is several tens of nanoseconds of accuracy, then maybe it's going to work. But if you're looking for high performance, then Sync-E might be a better choice.
Yeah. Okay. Great. Thank you very much. And
sure. Thank you very much for the opportunity to present, and we'll be happy to follow up with anyone that's interested in this.
Wonderful. And to everyone else, so hopefully in 2 weeks we have Alon from Keysight, and we'll see you in 2 weeks. Bye, everyone.
Bye.
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 Thank you. Bye.